back to the session, right. So, in the previous session we discussed a certain example of Nyquist plot. We have seen how to determine stability from Nyquist plot, okay. And then we had seen the basic introduction to the Bode plot. So, in today's session we will discuss all the steps of Bode plot and we will discuss one example of Bode plot, okay. Then that will help us to clear how we can plot Bode plot, okay. So, in the previous session we discussed about how to determine stability from Bode plot, how to calculate gain margin, phase margin from Bode plot. Okay. Last time we had seen if our system is stable, then gain margin, phase margin both will be stable. If system is margin stable, then gain margin, phase margin both will be 0, and if our system is unstable, then gain margin, phase margin both will be negative. So, this concept we had seen in the last session. In the last session we were discussing about the basic steps for magnitude plot. Okay. So, we had seen for this plot for k equal to 10 we were getting a plus 20 dB line, for k equal to 1 we were getting this 0 dB line, for k equal to 0.1 we were getting the minus 20 dB line. So, we had discussed this thing in the previous session, and whenever there is any poles and 0 at the origin, in that case we will get our magnitude like this. Okay. And when I want to convert in the dB, this expression would be like this. Okay. So, here this plus minus n will come here by property of log 20 plus minus n and log 10 omega. So, I previously told you this Bode plot we are plotting by magnitude in dB, and in the x axis we are plotting the frequency in terms of logarithm value, that is log 10 of omega. This is our frequency in the x axis. So, this whole term log 10 omega is given the frequency in the x axis, and this term is giving us a basic slope that will come in the magnitude plot. Okay. So, here I told you n, if n is 1, it means 1 0 at the origin, this will give us slope of plus 20 dB per decade. Why we are saying per decade, I will discuss later. So, whenever I put n equal to minus 1 pole at the origin, minus 20 dB per decade. When n is equal to plus 3, it means 3 0 at the origin, and this will give us plus 60 dB per decade. So, this will decide my initial slope of my Bode plot. Okay. If you can say if there is no 0 pole at the origin, so this will start by constant value k, c equal to 20 log k. If single pole at the origin, it will start from this point with slope of minus 20. If single 0 at the origin, it will start from slope of plus 20 dB. Okay. In the same way, if 3 poles or 3 poles at the origin, so it will start from minus 60 dB. So, initial slope will depends on location of poles and 0 at the origin. Okay. So, always remember, if there is no pole, then 20 log k will decide initial value, and you will get a constant line, right, if there is no pole and 0 at the origin. If single 0, it means initial slope would be plus 20 dB. If single pole is here, initial slope will start with minus 20 dB. This is the initial point which will decide by the poles and 0, and we can say that this poles and 0 is equivalent to integral and derivative part also. So, whenever I am saying single pole at the origin, it is equivalent to 1 over s, okay, integral part, and whenever single 0 at the origin, s equivalent to derivative d by dt. Okay. So, here I can say for Bode plot I have to consider the sinusoidal transfer function, it means sine wave as an input. For that case I will put s equal to j omega. So, s g j omega given by this, mod of this given by this, then I need to calculate this thing in dB. So, 20 log 10 of this is equal to given by 20 log 10 of 1 over j omega, and this is giving us minus 20 log 10 omega. Okay. So, this is the integral part, right. So, log 10 omega is the x and minus 20 is the slope. Okay. Just like you can see this thing in the previous formula, y equal to mx plus c. Okay. So, where m is the slope is given by this factor, x term is given by basically log 10 omega, plus c term is given by c equal to 20 log base 10 k. and this will decide the magnitude plot. Okay. So, here it means if integral term or 1 over s term is coming, it means my initial slope would be of minus 20 dB. Okay. In the same way, when we go for 0, g j omega is given by j of j omega, its mod would be given by this, then 20 log 10 of g of j omega, you can say this mod would be omega here, not j will not come here. Okay. So, this 20 log 10 would be given by this term, log 10 omega would be x term, and plus 20 dB will be the slope. Okay. So, why we are saying it is dB per decade. Okay. It means if frequencies, you can say if we do the frequency hopping in the x axis, we will get the multiple of 10, right. So, we can say our frequencies are in decade. So, decade is a band when we move from omega 1 to 10 omega 1. For example, I am having a two frequency, one is omega 1 and second is omega 2, and I would like to say their hopping, their distance is unity. It means if I move unity distance in the x axis, then what will happen? Suppose at initial position I was at omega 1, and in the new position when I achieve this value 1, I am at omega 2. Okay. So, I can say this difference is log 10 omega 2 minus log 10 omega 1, or I can say log 10 omega 2 by omega 1 equal to 1, or I can say omega 2 equal to 10 times of omega 1. It means if I switch a unity distance in the x axis, it is equivalent to movement of 10 frequency or 10 omega in the x axis. So, that is why we are saying our magnitude is changing per decade. Okay. This is the meaning, that is the reason behind using per decade in the slope. You can say we are saying plus 20 dB per decade, minus 20 dB per decade. This is the basic reason behind it. Okay. So, now if we are considering this term g j omega 1 over j omega, we will get here slope of minus 20 dB, and if I see the phase plot, this will gives me a minus 90, and my phase is not depending on omega. So, I will get a straight line in the phase. This is my x axis log of 10 omega, again this is my x axis log of 10 omega, and this line will goes to the infinity. Okay. In the same way, when we come for g j omega h j omega, so I will get my starting point from minus 20 dB, and we will get here a slope of plus 20 dB, and if we see phase for this case s is present, it means this will give us a phase of plus 90. So, in the phase plot, this is not depending on omega. So, here I will get a constant line around plus 90. Okay. So, I would like to know what would be the value whenever this magnitude plot crossing the 0 line. Okay. So, in that case what I will do, I will put my magnitude equal to 0 at this point to determine value of omega. Okay. So, here my magnitude is g j omega dB equal to 20 plus minus n log 10 omega. I will put equal to 0, log 10 omega equal to 0, or you can say omega equal to 10 raised to power 0 by anti-log process, and we will get omega equal to 1. It means my magnitude will be equal to 0 at omega equal to 1. Okay. So, whenever we need to know this point, evaluate magnitude equal to 0. So, in both the case here for 0, this line will cross 0 line at omega equal to 1. Okay. Now, we would like to see how to plot first order factor in Bode plot. Okay. So, G s is given by 1 plus s t plus minus n. So, I told you, you need to convert our transfer function in time constant form, that is 1 plus s t. So, plus minus n is the power. If n is positive, it means we are adding 1 plus s factor in 0. If n is negative, it means we are adding a pole 1 plus s factor in denominator, or we are saying it is acting as a pole. So, here this is a transfer function, generalized case I am taking it is plus minus n. So, whenever I need to calculate its mod, it is given by under root of 1 plus omega t whole square plus minus n. This term is in power. If I take 20 log 10 of, if you can say if I convert it in dB, 20 log 10 of this will come here, 20 log 10 of this will come here, and plus minus n will come here by property of log, and this is the expression. Okay. So, now we have to apply here certain approximation to draw the Bode plot. So, we are doing here a low frequency plot and high frequency plot. So, for low frequency I am saying omega is very small as compared to 1. Okay. So, I can neglect this whole term. Okay. So, here this will become only root 1, that is 1. If I assume n is 1, so I will get here 20 log 10 1, for n equal to 1, this is 0. It means in the magnitude plot for low frequency I will get this straight line at 0 dB. Okay. So, when I go for high frequency, it means omega t is too much higher than value 1, then my magnitude would be 20 log 10 plus minus n under root of omega t square. So, we can neglect here 1 because omega t is very high as compared to 1. This will be the term. After solving, this will become minus 20 log 10 omega t if I put here n equal to minus 1. Okay. It means I will get here a slope of minus 20 dB log 10 omega, we can say it will be on x axis. So, from this point I will get a slope of minus 20 dB for high frequency. So, basically this is what? This is the low frequency asymptote, and this one is what? It is high frequency asymptote. Okay. So, we are making this approximation. So, this is the asymptotic approximation, that we are getting the abrupt line. In actual system, if you do this plot, you will get here a curved line instead of this abrupt line. Okay. So, here what is happening? We are doing here asymptotic approximation, that is why we are getting this zigzag type of line, and we will get here a corner frequency term, the frequency which will separate the low frequency asymptote, that is this one, and high frequency asymptote, this one is known as corner frequency, and it is given by omega equal to 1 over t from this concept. Okay. You can say from here omega will be 1 over t, right. What about phase plot? If you see, for phase plot I will determine the phase from here 1 plus j omega t. If I assume here n equal to minus 1, so this will be 1 over 1 plus j omega t, and if I calculate its phase will be tan inverse of omega t. Okay. So, here what I will get for 0 omega equal to 0, you can say phase will be 0. For omega equal to 1 by t, phase will be, you can say, minus 45, 1 by t will make 1, tan inverse 1 would be 45, and whenever I make omega equal to infinity, then this will become minus 90, minus sign will come here in the phase, I forget here. Okay. So, this will be the phase will come. So, if I draw the phase plot, it will start from 0 crossing the minus 45 and go to the minus 90, and this will happen whenever we add single pole in the system. Okay. It means if I add a single pole in the system, then I will get a phase shift of 90 degree. So, always remember, whenever we are designing the system, you can say an analog filter, I would like to know how many poles are present here, then I have to see my phase plot, and then I have to see the change in phase. If change in phase is 90, it means single pole is present. If change in phase is 180, it means 2 poles are present in the system. Now, come for second order system or second order factor, right. So, here it is given by G s equal to h square plus 2 zeta omega n s plus omega n square plus minus n. Again it is power. If it is positive, it means this expression in the numerator and giving us 0. If it is negative n equal to minus 1, it means it is a pole, or sorry, it is a expression which will come in denominator, which will give us second order poles. Okay. So, here s equal to j omega you need to put, and you can take common omega n square. Okay. So, that you have to convert in 1 plus s t form, time constant form. Okay. And then you need to take magnitude mod of g j omega given by this factor. Okay. So, here for simplicity we can assume n is equal to 1. Okay. So, for this case again I need to convert this whole magnitude in dB to 20 log 10 of this expression would be given by this, and this plus minus n factor will come here by property of log, this is here. So, for simplicity I am assuming n is equal to 1. Again we will apply here approximation of high frequency and low frequency. So, in this case for low frequency I am assuming omega by omega is very small as compared to 1. Then what will happen? So, in this case this expression will come here. So, here this factor is very small, I can neglect this factor, I can neglect this factor because it is very small. So, this will become 1 only. So, log of 1 will be 0. It means for low frequency I will get here a 0 dB line, same that we were getting in first factor case. Okay. For high frequency omega by omega n too much higher than 1. Okay. So, mod of this is given by 20 log 10 plus minus n, same expression. Okay. And this is given by this, I am assuming n equal to 1 for simplicity. For high frequency this factor is very high as compared to 1. So, here higher factor we can neglect it. Okay. So, this will make expression like this, and further if we solve it, this will be square root will replace by square term. Okay. And this will become you can say 40 log omega by omega n if I solve it further. Okay. So, in this way what we are getting here, the slope of plus 40 will come whenever n is equal to 1, and slope of minus 40 will come when n is equal to minus 1. Okay. So, this will happen with quadratic factor, right. So, to determine the corner frequency we need to do what? We need to put we need to put our magnitude equal to 0. Okay. So, this will separate out the high frequency and low frequency as I am told. So, here my mod would be given by this, I need to put equal to 0, and we will get omega equal to omega n. It means for quadratic factor my corner frequency will be given by omega n. So, whenever s square plus 2 zeta omega n plus omega n square is given, you need to calculate omega n, which will gives you corner frequency. Okay. Always remember for quadratic factor. Okay. That is the frequency of oscillation is the corner frequency in second order factor. Okay. Now, phase calculation, phi is given by this term from previous expression. You can see if omega is 0, phi is 0, if omega is omega n, you can put here, phi is you can getting here, then phi is minus 90. If you put omega equal to infinity here, you will get phase is minus 180. It means you will get phase plot starting from 0, terminate at minus 180. If you see the magnitude plot, for low frequency we were getting 0 dB, for high frequency we were getting a slope of minus 40 dB when n is minus 1. Okay. If we say n is plus 1, so we will get a slope of plus 40 dB for n equal to plus 1, and this is a corner frequency omega equal to omega n. So, this will happen whenever we are assuming second order factor. Okay. Now, we will take this example of Bode plot, where we are getting g is equal to 5 s plus 4 s plus 0.25 s square plus 4 s plus 25. So, you can see 1 over s term is here, integral term, s plus 4 s plus 0.25 first order factor, s square plus 4 s plus 25 second order factor is here. Okay. So, first we need to convert in time constant form, 1 plus s t form, everywhere you need to calculate. After converting, this is my expression. Now, I need to replace s by j omega. Okay. So, here first I will convert this after putting s equal to j omega, I will obtain sinusoidal transfer function. Step 1, I need to start here with my initial point k. So, here k is coming 3.2, k equal to 3.2. So, c value is 20 log 10 k in dB, c equal to 20 log of 3.2. This is coming the 10.1 dB. This is my initial point in the Bode plot. So, I have to search the magnitude plot. I will see which is my point 10.1 dB. So, this is my initial point of Bode plot till now. Now, I have to see what would be my initial slope. Is there any pole at the origin? So, you can say 1 by s, yes, 1 by s is here. It means I will get here a slope, initial slope of minus 20 dB, right. If any 0 would be here, then we need to see how many poles 0 at the origin. Then remaining slope will be determined by first order and second order factor. Okay. So, here we need to replace this transfer function by s equal to j omega, and we will obtain this transfer function. Now, we need to arrange all the corner frequency in increasing order. So, whenever my first factor here single pole, you can say 3.2 over j omega, and this will gives me initial slope, and for value of k equal to 3.2, I had done this calculation in dB, and I am getting this is my initial point in the Bode plot minus 20 dB. So, my single 0 is here, you can say. So, first s plus 4 I will convert it 1 plus s by 4. So, s you can say 0 value that is coming from here would be 0.25. If I calculate this value of pole, it is at 4, okay. And here if I calculate it, corner frequency will be given by omega n is here 5. So, I can say my corner frequency would be 5. So, 1 0 is at 0.25, 1 pole is at 4, 1 corner frequency for second order factor it is at 5, 2 poles at 5. Okay. So, we need to arrange this corner frequency in increasing order, and depending on that we need to sketch our magnitude plot. Okay. So, here I am arranging those corner frequency 0.25 corresponding to the single 0, okay, and 4 corresponding to the single pole from factor j omega over 0.25 plus 1, okay, because this is j omega t. If you remember 1 plus j omega t, and corner frequency is given by omega equal to 1 by t. So, that is why it is 4. In the same way for double pole, we know this factor, we need to see omega n, it is 5. So, my corner frequency is here 5. Okay. So, whenever single 0 is here, we will get plus 20 dB slope. Whenever single pole is here, we will get minus 20 dB slope. When quadratic factor means 2 poles are here, we will get here slope of minus 40 dB. Now, start the magnitude plot. Okay. So, here my starting point is 10.1, I had done by calculation converting k in dB. My initial slope, it is given by here minus 20 dB, okay, and I have to start from here with a slope of minus 20 dB. I have to keep going till I found any corner frequency. When I found my first corner frequency, it is 0.25. I have to stop here. Okay. Now, I need to see what is the factor here. It is 0 or pole, it is 0. How much? Plus 20 dB. Okay. It means previously I was having plus 20. So, this previously I was having minus 20 dB slope. Now, minus 20 with plus 20 will gives me current slope of 0 dB. It means when I arrive at 0.25, I will move with 0 dB slope. I will move with here 0, no slope is here, I am moving. I will wait till I reach to the next corner frequency. So, here my slope is 0 dB. Okay. Whenever I arrive at 4, what I am observing? At 4, it is because of single pole and my slope would be minus 20 dB. So, previously it was 0, 0 will add with minus 20 and my final slope would be minus 20 dB. It means after this point at 4, I have to move with a slope of minus 20 dB. I will keep moving till I reach to my next corner frequency, that is 5. Now, what is happening at 5? So, at 5 I am getting a slope of minus 40. Previously my slope was minus 20, minus 40, minus 20, my final slope is here minus 60 dB. Okay. So, here at 5 I will get here a minus 40 more and total slope of minus 60 dB I am getting here, and it will goes like this. Okay. So, this is the magnitude plot. How we can go for phase plot? For phase we need to determine this expression. Okay. So, first minus 90 part 1 by s. So, you can say 1 by j omega, this will gives me minus 90, a constant slope we had seen in previous lecture. Okay. This is minus 90. Then my 0 factor will gives me tan inverse of this, my pole factor will give me this, and my quadratic factor will give phase like this. They are function of omega. We need to put omega equal to 0.25, 0.5, 1, 1.5, 2, 2.5, 3, 3.5, okay, and then we will get a phase plot like this, which will go in this shape. Okay. So, you need to do this calculation separately. For different value of omega, you will get the phase plot and then determine gain margin, phase margin to determine the stability of this system. Okay. In the same way, we would like to see one more example. What would be the Bode plot for this? It is basically G s equal to 25 upon S square plus 10s plus 25. So, we know that our corner frequency would be here 5 and it is of in pole. So, what I can say minus 40 dB slope would be there. Okay. So, how we can do this? We can convert in time constant form, then divide them into low frequency and high frequency as I am told. So, we will get our magnitude plot like this. This is 0 dB. Initially, we will get 0 for low frequency. For high frequency, we will get here minus 40 dB plot. So, here we can write 25 over s square over 25 plus 10 over 25 s plus 1. I will replace s by j omega 25 by j omega square over 25 plus 10 by 25 j omega plus 1. Okay. This will happen. Okay. So, now here this plot is coming for low frequency and high frequency. This corner frequency is 5, that is we can calculate from here. So, this is the plot whenever my zeta is equal to 1. What will happen if I reduce zeta? So, when I reduce zeta, I will get a bump type of structure at corner frequency. It is at zeta equal to 0.8. If I further make zeta equal to 0.2, it means more oscillation. I will get this curve like this, and for zeta equal to 0, I will get an open plot like this. So, this plot will happen for different value of zeta. In the same way, you will obtain the phase plot. Okay. So, this phase plot you can say and magnitude plot both are function of zeta in second order factor. Okay. So, this is about the Bode plot, which will help us in calculation of frequency domain analysis, which will help determine the stability of closed loop system by observing the open loop system. Okay. So, thank you for